Welcome back. Today we're going to be talking about the definite integral. And the definite integral is a pretty important topic in calculus because it really is answering one of the two big questions of calculus, and that is, how do you find the area under a curve? So if I were to draw a function here, so let's say I have this function f of x, and I've got a point A and I've got a point B. One of the big questions in calculus is how much area is there under the curve between A and B. So what is the area of kind of this shaded region in here, and how would we find that? And I've got to admit that this is one of the questions that really got me excited about mathematics and excited about calculus when I was a student, because my first reaction to this problem was, well, that can't be done. You can't find that area. It's curved on top. Like, the curviness makes it impossible. We're not going to be able to find the area of a curved region. I mean, when we're in geometry class in high school, you've got nice things like squares, and you've got rectangles, and you've got triangles, and we figure out how to compute the areas of these things, these different objects. But it's kind of like, if it's curved, you can't do that, right? Well, the answer is, well, you actually can. And that's what is one of the great things about calculus, is that we can find these interesting areas, all right? So that's the question that I want to kind of tackle today, is how do you find the area under a curve? Okay, so that's kind of where we start. And so let's talk a little bit more about that question. So let's say we want to do the following. So here's a little example for us. Let's say we want to estimate the area under the parabola y equals x squared on the closed interval from 0 to 1. Okay, so I'll just draw this really quick. I can draw it kind of big. Got some space here. So here's 0, right here, 0, 0. And up here is 1. And I'll draw a little dotted line to show us where we're at here. And I want to know, this is a parabola, right? Over here would be the other side of the parabola if we cared. We don't, because we're just interested on the interval from 0 to 1. And I want to know, okay, how much area is there under this curve between 0 and 1? Okay, so I'm trying to find the area of that shaded region. Well, you can imagine kind of going back to the beginning when people first started asking these types of questions. How much area is there in a curved space? And I think maybe the most basic shape that people ask this question about is a nice circle, right? So you have a circle, you want to know how much area is there inside of a circle. And you know that the area of a circle involves the number pi. Pi is a little bit complicated. So this isn't an easy question. And so how did people tackle this problem? Well, let me erase real quick here, and let's redraw this same shape. So we've kind of got this parabolic shape. Here's 1, here's 0. And one way that we could do this is we could break this up into some pieces and calculate the area of each piece. Now, one way I see really quickly that if I just wanted to estimate the area under this curve, I could use a triangle, right? I could kind of go, okay, here's a triangle, and that triangle is sort of like the area under the curve. Not exactly. We've got some space in here that's we're off by, but it would be an estimate. And what is the area of this triangle? Right here. Well, it's a half, because this is a 1 by 1 square, right? And this is half of that square, so the area is a half. Okay, great. That would be an estimate. It's not a perfect one. We could probably do a little bit better, so let's try. And so what people eventually did is they said, okay, there's another way we could think about this. Let's break that same area up into some pieces using rectangles. And at first it seems like rectangles might not be the best, but let me show you how it works out pretty well. So let's start out by dividing this up into 4 pieces. And this is at a fourth, here's a half, here's 3/4, here's 1. Okay, and so what I'm going to do is I'm going to use a rectangle at each of these points, and at 1/4 I'm going to go up to this point, and that's going to be my rectangle. So I get a little rectangle here. At 1/2 I'll go up to the functional value at 1/2, draw a little rectangle, and then fill this in, and I get my second rectangle. At 3/4 I do the same, and I get some area here. And then at 1 I do the same, and I get some area here. Okay, and if I wanted to, I could go through the process of actually figuring out what is the area inside of all of these rectangles added up. Really quickly, just because we haven't done this before, let's think about it for a second. The way that I would actually figure this out is the area, if this is my estimate, is going to be something like the functional value of 1/4 times that's the height of this rectangle right here, times the width of that rectangle. But the width of the rectangle is a fourth. Okay, so it's f of 1/4 times a fourth. And then I need to add on the second rectangle, which the height of the second rectangle is right here. That's the functional value of a half. And the width of that rectangle is right here, which is still a fourth. Plus f of 3/4, which is the height of the third rectangle. And then I need to multiply by the width of that rectangle, which is also 1/4. And finally, we get f of 1, which is this distance. So that's 1 times the width of that rectangle, which is 1/4. Okay, put this all together. Remember that this is the function here is f of x equals x squared. So f of 1/4 is 1/4 squared, or 1/16, times 1/4, plus f of 1/2 is 1/4 times 1/4. F of 3/4 is 9/16 times 1/4. And finally, f of 1 is 1 times 1/4. Okay, and we could add all of that up, and what would we get? So let's see. We could add it all up, and we would get 16 times 1/4 would be 64, a 64th, plus a 16th, plus 9/64, plus a fourth. Right? So what is that? So we've got 10/64, and then we've got 4/16 plus 1/16, so 5/16. How many 16s go into a 64? 4 of them. So this is 30/64. If you prefer, that's 15/32. Okay, so that's our estimate. if we just added up these 4 rectangles, we could get an estimate of what the area under this curve is. Again, it's not perfect, right? That's not a perfect estimation. And we could have done some things differently, okay? So we could have done it this way. We could have said, okay, here's my parabola again. We could have divided it up into 4 pieces like I did last time. But now instead of taking, last time I used the right endpoint to create my height. What if I use the left endpoint? So instead here, I'm going to use the left endpoint to create my height. So the first rectangle has no height. It's just a straight line. The second rectangle, I'll use this guy for my height. And I get that little rectangle. Then I use this guy for the next height, and I get this little rectangle. And then I use this one for my last height, and I get this little rectangle. Okay? And so now I could do the exact same thing, and I could get another estimate. Now, notice that the first estimate is higher than the actual area because it was above the curve. The rectangles were above the curve. Here, the rectangles are below the curve, so I'm getting a lower estimate. And the area, the actual area, is somewhere in between. Now, what if I wanted to get even closer? What I could do is, let's draw again. Here's my parabola. Here's 1. And instead of breaking it up into 4 pieces like I did before, what if I broke it up into 8 pieces? And now, let's say that we have some rectangles here. Now I've got this rectangle, here, 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 and finally here. And can you see, if you look at it carefully, you see that this is better than what we had before. Well, I could do it again. Instead of breaking it up into 8 rectangles, I could break it up into 16 rectangles. I could break it up into 32. I could break it up into 100. Excuse me. But I could keep going and going, and every time I get a little bit closer to the area. So the question is, I get it. Let's break it up into infinitely many rectangles. And now I have to say, well, be a little bit careful. If you add infinite rectangles, what would be the width of each one? The width would be 0, but 0 times anything is 0, so you get no area. So the only way that I can actually add these up is if I have finitely many rectangles. But I want the rectangles to get small. So what we're going to do is we're going to take the limit as the number of rectangles goes to infinity of a bunch of rectangles. Okay, so let me get a little deeper into this. I'll clear this out. And before we go any further, I need to talk about something that's really important, and that's the concept of a summation notation. So a lot of times I want to sum a bunch of things up, and I need a shorthand version to write it. So let's say we have some things to add, like A1 plus A2 plus A3 plus A4 plus and so on. And let's say we just keep on adding until we get to A sub n. Okay, so I'm adding up n things. And I want a better way to write that. Writing out this huge long list every time I want to write up a sum is not so great. So there's a notation, and what we do is we use a capital sigma. So sigma is a Greek letter, and we use this capital sigma to say add up. And what are we wanting to add up? We want to add up all these A guys. A1, A2, A3, all the way up to AN. So what I'm going to put over here is I'm going to say I want to add up the A sub K, but I want the K's to have different values. I want to start when K is 1 and add that guy, and I want to end when K is N. So the way that I write that is I say start when k is 1 and end when k is n. So what this is saying is add up all of the a sub k's, starting with k is 1, ending with k is n. So the sum k going from 1 to n of a sub k means a1 plus a2 plus a3 plus and so on plus a sub n. That's the basics of what we would call summation notation. So let me write that at the top. This is summation notation. And we'll use it a lot in this section. So let me write some other things with summation notation just so we can practice a little bit. All right. So first thing, using summation notation, we could just add up a bunch of constants using summation notation. It's not super interesting, but we can certainly do it. Let's think about this for a second. We've got the sum k going from 1 to n of, let's just say, the number 1. So this is saying add up when k equals 1, I add 1. When k equals 2, I add 1. When k equals 3, I add 1. And how many times am I going to add up 1? Until I get to n. So I add it up n times. And what's 1 plus 1 plus 1 plus 1 n times? It is n. So the sum k going from 1 to n of 1 is just n. Okay? So n is the answer. Now let's do something slightly more complicated. Let's look at the sum k going from 1 to n of k. And the way that I'd write this out is, this is when k is 1, I add 1. When k is 2, I add 2. When k is 3, I add 3. And so on. Da, 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 da. And finally, I add, when k is n, I add n. So I'm adding up the sum of the first n integers. Okay? So I'm adding 1 plus 2 plus 3, dot, 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 and so on all the way up to n. And it just so happens that the answer to this is n times n plus 1 divided by 2. All right. That's good to remember. Another one that's good for us to remember is the following. What if we want the sum k going from 1 to n of k squared? I could write this out again. This is 1 squared plus 2 squared plus 3 squared plus, and so on, plus n squared. And this just happens to be n times n plus 1 times 2n plus 1 over 6. Okay, the final one that I want to share with you that's going to be helpful to us is, what's the sum k going from 1 to n of k cubed? This is 1 cubed plus 2 cubed plus 3 cubed plus, and so on, plus n cubed, which is equal to n times n plus 1 over 2 quantity squared. Now, this is really interesting. Notice that n times n plus 1 over 2 is the sum of the first n integers. If I square that number, it's the sum of the first n cubes. That's kind of amazing, and if you get nothing else out of today, the amazement of that result should just shock you. But if not, we'll move on. This is just going to be very helpful to us when we're adding up a bunch of rectangles, because we have many rectangles to add, and we need to know how to add up large numbers. All right. So now that we know a little bit about summation, let's go back to what we might want to do to actually find the area under a curve. Okay, so I talked about we're going to add up a bunch of rectangles. So what I want to do is let's go back to my graph, and we have still our nice little parabola, and I said let's just break it up into a bunch of pieces. Okay, so what I want to do is, this is my number, I'm going to call it for now, just in general, this is A and this is B. This is where I'm going to start adding. B is where I'm going to stop adding. Okay, and then I'm going to break this into a bunch of pieces. Okay, so we're going to call the first hash mark, I'm going to call that x sub 1. The second one is going to be x2, x3, x4, and some more, until finally we get to the very last guy, B. I'm going to call him x sub n. A is going to be my x sub 0. Okay, so A is x0, and then I'm going to count up all these little tick marks until I finally get to x sub n. All right, so the question is, I'm chopping this up into a bunch of rectangles, and I'm going to take the functional value based on the right-hand side. So this is going to be my first rectangle. Okay, so here's my first rectangle I'm going to add. And the question is, what is the area of that rectangle? Well, it's the functional value at x1 plus the width of the rectangle. Now, the functional value at x1 is the following. Well, this is kind of interesting. See if you follow what I'm saying here. So I'm trying to find some area here, and the area is going to be approximately f of a plus delta x times delta x, where delta x is the width of the rectangle. So what I'm saying is, start at A, move over delta x, and take the functional value. That's the height. Then delta x itself is the width. And right now I'm assuming that every rectangle has the same width. Okay? So that's what I just wrote right here. That is just the area of the first rectangle. What would be the area of the second rectangle? Well, it would be f of a plus 2 delta x's times delta x. Why? Because if I start at A and go over 2 delta x's, that lands me right here. I take the functional value to get my height, and then I take delta x, the width, to get my width, multiply them together, and I get the area of the second rectangle. Plus, keep going. The third one would be f of a plus 3 delta x times delta x. And I think we get the idea. 1 delta x, 2 delta x's, 3 delta x's, take the height, then take the width, and we get our third rectangle. So this is the first rectangle, second rectangle, third rectangle, plus, and so on. And my very last rectangle would be f of a plus in delta x's times delta x. Okay, let's put this all together in summation notation. Another way I could write this is that the area is equal to the sum, k going from 1 to n, of f of a plus k delta x times delta x. This is a way of estimating my area within rectangles. Now, what if I actually wanted to get the actual area? So remember that this is kind of approximate because it's not perfect. What if I wanted it to be perfect? Well, I'd want the number of rectangles to go to infinity. So let's do exactly that. I'm going to clear this, And so what I want is, if I want actual area, then I want to take the limit as the number of rectangles in goes to infinity of this sum, k going from 1 to n, of this f of a plus k delta x times delta x. And this is technically how we take a definite integral. Okay, we might call this the definition of the definite integral. And what I mean by definite integral is I want to take the area under the curve. So this is how I do it in general. I add up a bunch of rectangles. That's always what it is. Anytime I take a derivative in this class, a definite integral in this class, anytime I do it in Calculus 2, Calculus 3, I'm always just adding up a bunch of rectangles. And that's really important to remember, that at the end of the day, calculus is about adding up a bunch of little rectangles in a lot of ways. Now that we know that, how does this actually work out to find the area under a curve? By the way, I think it's worth noting that delta x is always equal to b minus a, and b minus a is the length of the interval divided by n, because I'm dividing the interval up into n pieces. So delta x is just a fancy way of writing b minus a over n. All right. Now, let's go back to the original problem, and let's see how we would actually use a limit like this to calculate the area under a curve. So here's the example problem that I would like to do for you. So here's the example problem that I would like to do. So example. So let's use the summation definition of area to find the area under the parabola y equals x squared on the interval (0 to 1). Okay, so same problem we've been talking about this whole time. But this time I really want to get the real answer. Okay, so I want this area. So first thing we do is we're going to divide this up into n pieces. Okay, n equal pieces. And then I need to start writing this thing out. And my definition said the following. What I want is a couple things. First, let's remind ourselves, what is delta x? I just told you it's b minus a over n. Well, what's b in this case? On my interval, b is 1, the right endpoint. A is 0, the left endpoint. And n is just n. So I'm just talking about 1 over n in this case. That's my delta x for this problem. Okay. Then I should go back to my equation. The way that I'm going to find area is I'm going to find the limit as n goes to infinity of sum k going from 1 to n of f of a plus k delta x. Remember, that was the formula. A plus k delta x. What's a in this problem? We just said it's 0. So this is 0 plus k times delta x. But I just said delta x is 1 over n. So it's k times 1 over n times delta x, which is 1 over n. Let's rewrite. Okay, so this is the limit as n goes to infinity of the sum, k going from 1 to n, of f of k over n times 1 over n. All right. What is f of k over n? Remember, the function here is f of x is equal to x squared. That's my function. So if I take f of k over n, I just square it. So what I'm talking about here is this is just the limit as n goes to infinity of the sum, k going from 1 to n, of k over n squared times 1 over n. Okay, let's rewrite. This is the limit as n goes to infinity of the sum, k going from 1 to n, of k squared over n squared. That's a square right there. It looks terrible. Squared times 1 over n, which is the limit as n goes to infinity of the sum, k going from 1 to n, of k squared over n cubed. All right, now notice what is changing here. In this last equation I wrote, k changes. K is 1, and then it's 2, and then it's 3. The n cubed doesn't change. It's in every single term. And if something is in every single term of a sum, I can factor it out. So constants can be factored out of summations. So let's do it. If I do, I'm going to write this as limit as n goes to infinity of the 1 over n cubed can come out of the sum. And then I have left over sum k going from 1 to n of k squared. Now, this sum that's sitting right here, I already told you the answer to it. I told you what the sum of the first n squares are, and so let's write it. We've got limit as n goes to infinity of 1 over n cubed, and the sum of the first n squares is n times n plus 1 times 2n plus 1 over 6. What is that limit? Well, it ends up, now this is just a simple problem of taking the limit as n goes to infinity of a rational function. So what I ask is, what's the highest power of n on top and bottom? Well, on the top, if I multiplied it out, I'd get an n cubed. On the bottom, I'd also get an n cubed. What would be the coefficients in front of the cube? Up here, I've got an n times 2n. That's a 2n cubed. And on the bottom, I have an n cubed times 6, so 6n cubed. So what's the limit going to be? 2 over 6, or 1/3. And 1/3 is the actual area under that curve. So we did all this work to figure out how much area is there under the parabola y equals x squared between 0 and 1. And we figured out there's exactly 1/3. And if that doesn't amaze you, I'm speechless. I'm speechless if this isn't just exciting news to you that we can find the area exactly under a curve. So this is really great. Let's look at some homework problems and kind of dive in a little deeper into how you would actually use this knowledge.